Quick one. What's the greatest integer of negative 2.3? Don't overthink it, just answer in your head. Got it? Hold that thought, because there's a decent chance you're wrong, and it's not your fault. There are 5 functions that chop up the number line, and honestly they're all the same idea wearing different hats. It's not negative 2. It's negative 3. And if that caught you off guard, here's the uncomfortable bit: every greatest integer question you've ever attempted was basically a coin flip. You got the positives right and the negatives by luck. Same trap hides in all 5 of these symbols. So here's your toolkit. 5 symbols. Modulus asks how far from 0 you landed. Signum asks which side. Greatest integer, the floor, asks which whole number you stepped past. Fractional part, how far past it. And ceiling, which integer you're heading toward. Same number line, 5 different questions. That's the whole trick. Here it is. It just drops the decimal. That's the rule almost everyone walks into the exam with, and I get it, it feels clean, it feels mechanical, it feels safe. Number goes in, decimal falls off, answer comes out. And it works. Right up until it really doesn't. Watch it succeed first. Greatest integer of 2.3? Drop the decimal, you get 2. Correct. 0.23? Drop it, you get 0. Also correct. Every positive input behaves exactly the way the shortcut predicts, which is precisely why the habit sticks so hard. Now negative 2.3. Drop the decimal, you'd get negative 2. But look where negative 2 actually sits on the line, it's to the right. It's bigger than the input. And this function is defined as the greatest integer that does not exceed x. An answer above the input isn't just unlikely, it's structurally impossible. So negative 2 is out. The real value is negative 3. Here's the fix, and it's not what you'd expect. Don't memorize a special rule for negatives. Throw out the decimal thinking entirely. Every one of these 5 functions is asking the exact same thing: where does x sit between 2 consecutive integers? Once you picture that, the negative case stops being special at all. So let's actually picture it. Take any real number you like. Any one. Drop it on the number line and it lands somewhere, and wherever it lands, it's between 2 consecutive integers. Call them n and n plus 1. Doesn't matter if x is positive, negative, huge, tiny. It always lands in exactly one of these gaps. Move the dot anywhere you want, that fact doesn't change. And that's single landing? It's the whole video. Because now every function is just a different question about that one landing. How far from 0 did it land? That's modulus. Which side of 0 is it on? Signum. Which integer did it land past? That's the greatest integer, the floor. How far past that integer did it go? Fractional part. And which integer is it heading toward? Ceiling. 5 questions. 1 dot. 2 of those questions fit together beautifully. Look at the segment. You've got the whole part you've already passed, that's the floor, n. And then the little leftover bit from n up to x, that's the fractional part. Stick them together and you get x equals floor of x plus fractional part of x. The whole part you've passed, plus how far you're into the next one. Simple. But does it survive a negative? Now the real test. Drop negative 2.3 on the line, it lands between negative 3 and negative 2. Floor steps down, so the whole part is negative 3. The leftover? Positive 0.7. Add them, negative 3 plus 0.7 is negative 2.3. It works. But only because the floor went down first. Drop the decimal instead and the whole thing collapses. That's modulus. 2.3 and negative 2.3 are both exactly 2.3 units from 0, same distance, opposite directions. And modulus doesn't care about the direction. It throws it away and keeps the size. That's the entire job. Which means whatever you feed it, the output is never negative, and that shows up immediately when you graph it. 2 straight rays glued together. For x greater than or equal to 0, y equals x, a clean 45-degree climb to the right. For x below 0, y equals negative x, climbing left at 135 degrees. Both meet at the origin. The whole graph sits on or above the x-axis, exactly like the definition promised. But zoom into that join point and something interesting happens. It's a genuine sharp corner. Not a smooth turn. Watch the tangent try to roll through it and just snap. The angle jumps instantly. And that's the bit that gets examined, because a corner is exactly where a function stops being differentiable. Remember this point. There's more to modulus than the graph, though. Domain, all reals. Range, 0 to infinity, including 0, the output never dips below the axis. Parity, even. Symmetry, about the y-axis, which you can literally see in those two mirrored rays. That's modulus at a glance. Now, what happens when you put it inside an inequality? Two inequalities you want cold. Modulus of x less than or equal to a? That traps x in a band, everything from negative up to a, one solid stretch. Flip the sign, and x gets shoved out. Greater than or equal to a splits into two pieces, x below negative a, or x above a. One region becomes two. Trapped inside, or pushed out. And then the triangle inequalities, which you want cold. Modulus of x plus or minus y is at most modulus x plus modulus y. And it's at least the absolute difference of the two moduli. Upper bound, lower bound. Both of these were verified numerically across 200,000 random pairs, they just hold. Okay. Modulus asks how far. What asks which way? Signum. Defined as modulus of x over x, whenever x isn't 0, and set to exactly 0 at 0. Positive input? You get 1. Negative? Negative 1. Sitting on 0? 0. It's the perfect mirror of modulus, where modulus threw away direction and kept size, signum throws away size and keeps direction. And the graph shows that starkly. So the signum graph is barely a graph. Two flat rays plus one lonely dot. Right ray sits at y equals 1, left ray at negative 1. And those hollow circles at 0, 1 and 0, negative 1? They mean approached, never reached. The filled dot at the origin is the actual value, signum of 0 is 0. 3 outputs, forever. The entire range is 3 numbers. That's it. Negative 1, 0, 1. Feed in 4.7, negative 102.3, 0.0001, 88.8 doesn't matter. A million different inputs and you still only ever get 3 things back. Read it as a direction detector. And notice continuity snaps clean in half at 0. So think of these two as a matched pair, not two separate topics. Modulus asks, how far from 0? Signum asks, which side of 0? Neither one knows the whole story on its own, but together, between them, they carry every bit of information contained in x. Which means you should be able to put them back together and get x back out. And you can. X equals modulus of x times signum of x. For every real x, try 5, 5 times 1, 5. Negative 5, 5 times negative 1, negative 5. 0.7, negative 0.7, same deal every time. Size times direction rebuilds the original number. It's a genuinely nice sanity check. Now back to that staircase. So here's the whole floor function in one line. If x sits between n and n plus 1, floor of x is n. That's it. Notice the dot on n is filled, the one on n plus 1 is hollow. And look, you step down, not toward 0. That's the trap. Negative 8.0725 steps down to negative 9. So watch what the floor function actually does. Between negative 3 and negative 2, every input maps to negative 3. Flat. Then at negative 2 exactly, it jumps and holds negative 2 until just before negative 1. Step, jump, jump. That's the rule n less than or equal to x, less than n plus 1, drawn out. A staircase, running forever both ways. Zoom in on one step. See that solid dot at x equals 1? That value's included. The hollow circle at x equals 2 isn't. So the rule n less than or equal to x, less than n plus 1 means the floor is 1 across the whole stretch, then snaps up the instant you hit 2. Closed left, open right. The jump happens exactly at the integer. Recomputed from the definition, not the shortcut. 2.3 lands between 2 and 3, so floor is 2. 0.23 lands between 0 and 1, floor is 0. And 2? It's already an integer, it's sitting right on the tick, so it just stays put at 2. All fine so far. Then there's this one. Floor of negative 8.0725. Drop the decimal, you get negative 8, and negative 8 is bigger than negative 8.0725. Not allowed. This function can never exceed its input. So it steps down. Negative 9. That's the whole video in one example, honestly. Down the number line, never toward 0. So what happens when you negate inside a floor? Depends entirely on whether x is a whole number. If x is an integer, the floor of negative x is just negative the floor of x, clean. But take 2.3, floor of negative 2.3 is negative 3, while negative floor of 2.3 gives negative 2. You need that extra minus 1. The branch flips exactly at the integers. 2 floor rules worth carrying. Add a whole integer, and the floor just shifts by that integer exact, no drama, the staircase slides sideways. But add 2 reals and it's an inequality, not an equation. Try 0.6 plus 0.6, floor of 1.2 is 1, while each floor is 0. 1 beats 0. Fractional part is defined as x minus the floor of x. That's the whole definition. And notice what it forces, the result is always at least 0 and always strictly less than 1. 0's allowed. 1 is not. And that's true for every real input, positive, negative, doesn't matter. Which gives the graph a very particular shape. So don't define the fractional part. Build it. Take the line y equals x, lay the staircase on top, and subtract. What's left at each integer? The gap between line and step, a ramp climbing from 0 up toward 1, then snapping back. That's your sawtooth, period exactly 1, and it fell out of the subtraction. Range is 0 up to but never touching 1. Zoom into 1 ramp, 0 to 1. Filled dot at the bottom left, hollow circle at the top right, it climbs toward 1 but never gets there. And because the leftover resets every time x crosses an integer, that single ramp just tiles forever in both directions. Period, exactly 1. It reaches 0, never reaches 1. Which trips people up on negatives. So what's the fractional part of negative 2.3? Your gut says negative 0.3. Nope. The fractional part is never negative, it lives in 0 up to 1, always. Run the definition x minus the floor. That's negative 2.3 minus negative 3, because the floor steps down to negative 3. 2 negatives, and you get 0.7. Sitting right where it should. The reflection rule, fractional part of negative x equals 1 minus fractional part of x, geometrically it's the sawtooth mirrored, and you can sort of see why it'd work. But this rule comes with a condition attached, and that condition is where the trouble lives. Park that, we'll come back to it hard. First, the fifth function. The ceiling. Smallest integer not below x. The rule mirrors the floor exactly. If n is less than x, which is less than or equal to n plus 1, then the ceiling of x is n plus 1. Hollow on the left, filled on the right, flipped from before. And instead of stepping down, you always step up. Same staircase, opposite direction. And I mean that literally. Here's the floor staircase, dimmed. Now draw the ceiling on top and it's the same shape. Same steps, same heights. The only thing that changed is which end is hollow and which is filled. Open circle on the left, closed on the right. If you can draw one of these staircases, you already know how to draw the other. So let's run them side by side. Same inputs, both functions. 2.3 of floor gives 2, ceiling gives 3. 0.23, floor 0, ceiling 1. Negative 0.6, floor negative 1, ceiling 0. And the big one, negative 8.0725. Floor steps down to negative 9. Ceiling steps up to negative 8. Clean, opposite, exactly as defined. There is one case where they agree, though. Here's the clean way to see both staircases at once. Write x as I plus f, a whole part and a leftover. Floor keeps I, ceiling hands you I plus 1. But that only works when f is genuinely non-zero. If x is already an integer, there's no leftover to argue about, and both functions just give you back x. Okay, here's one that bugs me. Flip through textbooks and reference sites and you'll keep hitting this: the fractional part of negative x equals 1 minus the fractional part of x, valid if x is an integer. It shows up in a lot of otherwise reliable places. And it's the kind of thing a reread never catches. So let's actually test it. So test it. Set x equals 2. Left side, the fractional part of negative 2 is 0 and negative 2 is an integer, there's no leftover. Right side, 1 minus the fractional part of 2, which is 1 minus 0. That's 1. The rule is now claiming 0 equals 1. And it's not a fluke every integer from negative 20 to 20, all 41, fails. Flip it. The rule is valid if x is not an integer. Check it at 2.3, fractional part of negative 2.3 is 0.7. And 1 minus fractional part of 2.3 is 1 minus 0.3, also 0.7. Agreed. Checked against 200,000 random non-integer values, 0 failures. So where did the bad version come from? So where'd that bad condition even come from? Look at the floor rule. It splits, negating x gives minus the floor when x is an integer, minus the floor minus 1 when it isn't. Somebody pulled one strand out of that two-strand rule and grabbed the wrong one. The fractional part version needs the not an integer branch. Steal this habit. When a rule shows up with a condition attached, find the boundary case that condition names and just plug it in. For everything on this page, that boundary is the integers. That's where a misstated condition falls apart, like it did at x equals 2. 1 substitution. 5 seconds. And you never walk into an exam carrying a broken rule. Okay, screenshot this one. All 5, same input, negative 2.3. Modulus gives you 2.3. Signum, negative 1. Floor steps down to negative 3, ceiling steps up to negative 2, and the leftover is 0.7 positive, always. And the endpoints column is the part people lose marks on. Floor is closed left, open right. Ceiling's the mirror. Sawtooth, closed bottom, open top. Whenever your input is negative, ask whether your answer is on the correct side of it. Floor can never come out above x, ceiling can never come out below it. And fractional part can never be negative and can never reach 1. That's the 5-second check. Any answer that breaks one of those three is wrong before you've verified anything else. You don't even need to redo the arithmetic, you just know. So that's it. One number lands between two integers, and 5 functions just ask 5 different questions about that landing. How far from 0, which side, which integer you passed, how far past, which one you're heading toward. Stop thinking about decimals and the negatives stop being scary. If checking rules instead of just repeating them sounds like your kind of thing, there's plenty more coming. Follow along.